Right, we'll get started. So we have a few slides from lithography 1 and then we'll get into exposure and optics. So again, term paper is due Monday, submission is open. Rubric sample I'll definitely upload today, rubric sample and the previous lecture. So this, I was working on it to fine tune it to make it more comprehensible for you guys, so I'll get that done. So we were at exposure, development, and after development we do a bake and we inspect. What are we looking for? Before we bake, we inspect. We are looking for defects, we are looking for tolerances, looking for quality of the resist, that it is completely gone from places where it's not supposed to be and it is covering everywhere that it is supposed to cover. And that would mean that there can be places where photoresist fails, and failing can be due to many different types of reasons. Some of the common defects are scratches on substrate, which would cause less adhesion of resist at that place. It may be, there can be physical bubbles left in the resist itself. It can be dirt or any, contamination that might have been left on the substrate before we did spin the resist. And so there is a whole long list of reasons why a resist or a pattern might fail, or what we call lithography run might fail. We look for edges, that they are good, and once we are concerned about edges, there's an important part that the corners should also be good. So corners are important because there is much more going on at a corner when we do the exposure. They might turn out to be something which is not exactly sharp. We'll see how we can do something about it. Critical dimensions are good. What is critical dimension? Let's revisit again. What is critical dimension?
Feature size.
Feature size? Yes, of course. Everything has a size and every feature has size, but what is CD? The smallest
distance that you can specify without losing the resolution.
The smallest feature size you can?
In
pattern?
Without losing the resolution.
Without losing the resolution for a given technology, right? So for a given technology means for a given mass, given wavelength, given resist. So all those things go into that process, and so we can make a very small feature, but our CD may not be the smaller size. CD is what, as a designer, I have designed the smallest feature on that mask, right? It may be still, of course, it has to be bigger. It may be way bigger than what the smallest feature we can make with that technology. Right? But for me, in that mask, I have I have a line. Smallest line is 3 micron wide, and that is my CD. But with that technology, with that light, with that mask, with that resist, I may be able to make even smaller than that. But for that mask, my CD is 3 microns. So I have to know where to look for it. So I'll go looking for, scanning for that smallest feature I had. So if that comes out good, yeah, that gives lots of comfort that the bigger one would have come out good. So we make sure that they are CDs are fine, so there can be multiple shapes, multiple features, different variety of shapes of those features at that size, which we want them to come. Maybe circles, maybe lines, maybe distance between two lines. Not the line itself, but the pitch, but how often. Yeah.
The node is different from the CD?
Okay, so CD is my design.
So
Right?
CD is for mask and mode is for the wafer. That's how.
No, CD is my design. For that mask set, what is the smallest feature size I have made. But node or that technology can define a smaller feature than that. But I may not want that small of a feature in my mask set or my design of devices that I'm using. Right? So with a node, we make those devices or those gate lengths which are small. But that might not be the CD for all the masks levels. At a different mask set, my CD may be a different feature which is larger.
So your CD is the smallest feature on the mask, not on the
On
wafer.
that one lithography run that you're doing, on that one exposure that you're doing. So that's a critical dimension of that mask.
So it's of the mask, not
It's-
of the wafer.
When you say of the mask, I say of the pattern, because the mask may be stepped down 10 times. So what comes out on the resist itself is my CD. On the mask, it may be 10 times larger if I'm doing projection lithography and I'm scaling it 10 times down, but I don't call it mask. I call the pattern that's been registered. So that brings the notion of the size on the mask and what we register,
Okay.
right? So we are going into registration because that's something which we do in alignment. We have to, when we are doing alignment, we generally saw what is alignment. So alignment is bringing them together, right? But then once you push the pattern and exposure happens and we develop, then we have to see what have we got registered on the resist, which may be different because of the play in the machine.
Right. So, okay, what gets registered on the resist is your critical dimension.
Right.
But it's not necessarily the dimension of the device. It does not have to be.
No, it may be at a different level. Gate level mask is the most critical, right? Where we have the smallest feature. There I'm really careful. But if I'm running contacts, right, or interconnects, I'm more concerned about the line, the integrity of the line and length that it reaches. It would be a lot bigger in width, but I would be more concerned that it's not metal is not thin at any place, because that's going to result into failure. I'll be concerned about overhangs of metal. We'll see what is overhang next slide, which comes from left off. So registration is within limits. So I align, and then we expose and develop, and that process is registration, right? So it's like I have my, if you guys have seen those rubber stamps they used to use, especially in post offices, still they use some places. So you align it, but then what you get is registration may be a little out of place where you actually wanted it to be, right? We see that once we do those thumbprints, now it's all electronic, but a few years back we had to put ink on and then we align our finger, but then once you push it, then you figure, oh man, it's registered, still a little away. So registration and alignment are two things. Of course, registration is a function of alignment. How good we align. So there we have to make sure it's within tolerances, within limits.
So I have a question. Why would bubble and scratch better for resist quality? Like we're gonna remove
So
registration.
if I had a bubble and I did my exposure, my development, I will see some pictures also. How would these translate into defects? So say I had a line which was supposed to go straight, and then I had a bubble in resist. So what I will end up is a line to translate into a line, something like this. If I had this embedded bubble in resist. So these are multiple types of defects. We'll see defects much more closely in next few slides. So once we do hard bake, so we remove all solvent. So we want it to solidify. That makes the adhesion really good. It makes photoresist really hard for etching, to withstand etching, and reduces any holes that may be there in the resist. pinholes is a term you might want to get used to. Pinholes are not just a feature of resist. Any film we deposit or grow or however we get on the surface, if it has mechanical defects where we have very small cracks or openings, we call them pinholes. Pinholes are small round shaped defects which may go all the way or which may not go all the way, right? But what they're going to do is when you do harsh treatment, they're going to become big and they're going to go all the way. So they're going to result into defect at that place where resist was supposed to cover everything. How do we look at pinhole? How do we figure out there is a pinhole?
With an electron microscope?
Electron microscope, yeah, that can, but we don't know where to look for it. It can be anywhere. It's a defect, right? There's no specific place.
You pass light through it
Pass light through it.
and then see the reflection pattern.
That the pinhole may be smaller than the wavelength of the light itself. So, but there different pinholes and different materials would require different techniques. How do we figure out for the defect of pinholes, right? So, for resist, there is obviously no way to find pinholes. It would come out only as a defect once we are done with the treatment, whatever we are supposed to do, right? In etching, it will come out a small pit in the substrate, right? Because it was, if I had this opening for etching and I removed my whatever was there silicone all the way, right? This would result into small pit at the surface, right? So that will tell me the resist at that point was not completely intact. So there was pinhole. The defect smaller, too small that even an electron microscope would be almost impossible to find out. Yes, I'm not saying my electron microscope cannot look at small features, but you don't know where to look for, right? Unless those pinholes are everywhere. So hard bake in this case would re-melt polymer there to heal those mechanical defects. And yeah.
Do you ever hard bake past the glass transition temperature, or do you not want to vitrify the photoresist?
I think this temperature is above TG. Glass.
So it does vitrify.
Yeah, yeah. Because we want it to become really glassy, become really hard, so it can withstand the etch processing after it comes after. So it says it's typically close to the glass transition temperature of the resist. And we do deep UV exposure also to harden the resist, to increase the survival. Process called lift-off. What is lift-off used for? Pattern, metal lines, right? So metal interconnects. Ideally what happens is we would put resist down, we will put metal all across. These colors are not coming through. And we should get rid of resist. That leaves very fine lines with us. So they leave these, but this is ideal case. What actually happens is we have coverage of metal on, for the contrast doesn't give us these edges which are perpendicular, right? So they give us slanted edges, and then metal covers everywhere, right? So metal would have some fine and thin presence at the edge as well, right? So even if we have high contrast resist, there will be still some that will be left behind. So once you get rid of resist, what we get is overhang, which means the line width is not uniform. The line has extra material, which may result into shorts, which may come off later on, and fall somewhere in between two lines and make them short, which may get into oxide region or silicon region and result into electrical failure of those devices. We want to get rid of this. And what we get is our lines are not continuous. They might become wide or small unknowingly. What we do is we do something called a chlorobenzene treatment, which makes photoresist hard at the top. What it results into sort of a mushroom shape of resist where the metal falls without making those side walls. Right? So what we end up with, so it serves not only the metal lines are well defined, it gives us this solvent seeping place also to dissolve resist and to remove metal from everywhere. Right? So it's called lift off and chlorobenzene treatment lift off. That's how we make those long lines.
How do you control the overhang width? How much it extends out?
How much it extends out?
Like that mushroom shape, how do you control it?
Experiments. We know then for how long dip in chlorobenzene, for how thick of resist will give us what kind of tolerance. Right? So these are very well established process and how long do you expose? Because chlorobenzene reacts with resist and makes it hard. Longer you do, the deeper it will go into resist. So there will be a deeper layer of resist that will become hardened. It's your call that how deep you want to go. So that decreases the development rate there, and just the top layer of the resist has reduced development rate. So what we get at the end is a very well defined line.
Can you use a lift off other than metal?
Yeah, you can use lift off for anything. It depends on if you want to make a line or a feature, then you can do lift off for almost anything.
But why we usually prefer the metal material, not the
Because if you want to etch metal, you'll have to use very rigorous recipes. You don't want to do that. Right? There can be another way. You make a metal line and do lithography and etch metal from where you don't want it. That should have been another way of doing it, right?
Since lithography is more compatible, I guess.
Yeah, in that case also you would do lithography and then you would etch away metal from where you don't want it, right? But etching metal is those reactants will be very vigorous. And you'll see we use chemicals to etch metals. We do that, but they are very highly concentrated acids that we use. Why gold is expensive? Really?
Because it doesn't react with other materials.
It doesn't react with it. We call it noble metal, right? But bad news, we can etch gold as well. It's a chemical, a mixture of chemicals, acids basically. They call it aqua regia. Aqua water regia, I don't know what is that. So that's a very, very dangerous combination of sulfuric acid, hydrochloric acid, and I think nitric acid as well, which can etch gold as well. So, but those are expensive chemicals. So instead of doing etching of metal, I would rather do lift off.
Etching of English should be easier than any other thing.
Pardon?
Etching of gold should be easier than any other thing because it doesn't react, it shouldn't stick on.
Yeah, that's another thing that how does it stick to silicon? We don't stick gold directly on silicon or silicon dioxide. We use a sticky layer. We use a very thin chrome or titanium layer, which sticks well both sides.
Bonding, like bonding.
Bonding? So we evaporate, that's a sticky layer. We evaporate. So whatever method we use, mostly it's evaporation, physical evaporation. So, or E-beam evaporation specifically. So what we do is we always deposit a thin layer of titanium or chrome, and then we deposit metal. So in any case, the bottom line is I can define the same lines using lithography and etching, right? Or I can define same lines by doing lift off. Lift off, all I need is a solvent that can dissolve photoresist, right? Acetone can do that. But if I want to do etching of metal, it requires much more expensive and dangerous chemicals to do. We can do etching with reactive ion etching as well, but then again, the recipe requires much dangerous and expensive processes to do that. Right? So this will be revisiting resist properties and all those over and over, but let's now focus on optic side of lithography. Right? Because we have this appreciation now that lithography is not just optics or not just resist, they all come together. They have all, as a designer or as a process engineer, I have to know all those things. The energy that I use, what kind of resist I need, what are the issues with thickness, how do I apply resist, how do I do development, but what kind of light do I use and how do I register those patterns, and what does it take to get my light right to do that. So from optics point of view, resolution, registration, CD, and throughput, these are the important things. So resolution is how small of a feature size I can make, right? So minimum feature size that a technology can make. It's not CD. CD would be what we have discussed already before the rest of us join us. So CD is slightly different concept. So if you have to differentiate between CD and resolution, it should be clear. Now we align, we know technology, we know size, we know our mask, we know what we can produce with this, but what we actually get after development is our registration, right? And that again is now a factor of many things. So, and that has to be within tolerance of our previous, whatever features were there from previous mask runs. And then we have to see that they are within precision, within accurate size. So if I have 5 micron feature and I'm out by 5 micron, my lithography is failed. So I have to make sure that size is accurate and it's within tolerance. So that's the difference between dimension control and registration. And how quickly can we get our wafers out, right? From industry point of view, it's important to push as many wafers as quickly we can. Right?
Can you explain a little more pattern registration and dimensional control? I think both of them is dealing with accuracy.
Yeah, so one is, so registration, we are worried about the pattern which were there before. So we align our new mask, right, and then we expose. We develop and then we see, are we on top of our previous? And we also see, okay, we are on top, then we see our size of our feature is what we want it to be, right? That one is registration, the other is the device, the dimension of the feature. Is that within tolerance or not? Right. So, I'll tell you, a machine with 1 micron error in registration is fine if my feature size is 10 micron, right? It's just 10%. But if my feature size is 5 micron, my registration error is now 20%. So it keeps on going up. I have to inspect to see my registration is good. Now, both of these things depend on different things. My dimension control is an entirely different, has different issues in it if it's not coming the size you want, right? You know that. The internal reflection, resist, overexposure and underexposure, overdevelopment, underdevelopment can be other reasons. than the pattern registration.
Which is more difficult, pattern registration or dimension?
Think about it. If we go smaller in size, what is more important?
Dimensional control, but even pattern registration would be difficult because
Pattern registration. So getting it exactly where the pre is, that has been automated now. That is, those machines can move in within nanometer precision, especially when we are doing step and repeat. Right? So it's the feature size which is important.
So pattern registration is kind of standard, like you don't have to worry about it.
Yeah, because what we do here is where we move things, but what industry does is where there is only the projection system is stepping. So your step is known. So you know the error in your step. So it's nothing where things are moving up and down, they're just moving laterally. But what we do in contact lithography, where we have the light source come up and then do the flash. So registration error probably not as important as the dimension control. Because dimension control has this whole lot of other issues where your wavelength is important, your resist, internal refraction is, so it's much more involved to do this right than have this right. We have seen this before, we'll revisit this. What ideally we want is this. That I have my reticle of mass, right? My light passes through only this region. What I should get is this step function. Step function. But unfortunately, light travels in. How does light travel? Pardon? Divergent. How does light travel?
It diffracts around
How does light
corners.
travel? Rays.
Spreads.
Rays. Right? So that's why we define those arrows to show light travels in rays. So those are when they travel through and constriction and opening, what we get on the other side is diffraction, what is named after Bragg's diffraction, right? Where we have those lights going in all directions, especially at the edges. Right? They don't give us this, they give us this. So they give us a maxima of light intensity and trailing edges. And when we push down the wavelength, those trailing edges get further apart. Right? So see that becoming more spread out from the center of image. How would that translate to contrast? How would that translate to contrast? We have been grinding this concept for last 2 lectures. Of course, there was a break in between.
No, the diffraction is contrast.
Just look at this guy and see how it would contrast. If I push my wavelength down, what happens to my contrast? Decreases. Right? And by that, what's happening to my resist wall is becoming inclined, because now much more intensity is falling outside of where I wanted it to be. Right? So this would translate into something where I wanted this to be like this, and what I get is something like this. Just because much more light is hitting here also, because of that concept called Bragg diffraction. Right? So we'll look at this guy. So what would be the critical dimensions we'd be worried about? Thickness of resist, diameters of holes, widths of line, spacing between lines, and for any feature, the angle of the resolution, right? The angle of the exposed feature. All these things, or some of these things will define, or maybe one of those things will define a critical dimension. Right? So when I'm done with my exposure and developer, what do I look for? First thing, I want to go look for CD. That has registered accurately or not. So this guy is gonna. So if I don't get my light to have as close of my profile as a step junction, I will screw up one of those. Right? Why does it happen? It happens by light which have two components, E and B. And as they travel in x-axis, they are, what are they doing?
Orthogonal to each other.
They are orthogonal to each other and
Oscillating.
right? So they are, if one is maximum, the other one is
The one is maximum too, but in opposite direction.
the opposite direction. So they are orthogonal.
In 90 degree apart.
So they are, if they are in phase, they should change same, right? So they if one is at maximum, the other one is also at maximum, unless there is a polarization where one will go out of sync. But E and B, so one is, how do we define E and B?
Electric field and magnetic field.
Electric and magnetic field. So both of them undergo changes once they travel through a slit, an opening, and what we call that? Huygens source. So what we get is this kind of diffraction. Change color. It's too slow. It doesn't want me to do anything. It's not. So they travel, and once they go through a slit, the straight line behavior changes. This is called Huygens principle, and this simplifies our understanding of light going through a slit. So after the light goes through a slit, what we get is a profile, something of intensity, which looks like this, right? And these ripples are basically a result of what? Interference, right? Because now, instead of a straight line, we are seeing multiple sources emitting the light in different directions, and they result into maxima and minima, local maxima and local minima. And we can model these arrows as independent light sources, because one light is now going in every direction, so they are then called secondary waves or wavelets coming from that aperture. How do they restrict, or how do they come into play with what we are doing? We are doing many slits in our masks, right? So these are all small openings, transparent openings, and light goes through. So not just the. So that discussion will come later on, that how small of a feature can we make with respect to the wavelength. But before that, we are now having these number of sources of light, of wavelengths, which would be now interfering with each other. And what we get on the surface will be something which will have this kind of shape, and as we move the mask away from the wafer, these become larger wavelength. So these interferences become large in wavelength. So what we get at certain distance from there is what is called Fraunhofer region in optics, is instead of that step junction, a distribution, which results from interference of those individual light sources. Right? So our image is now a broad central region instead of a step junction, a step function. How does that change? That changes everything. That changes our resolution limit, right? Which is defined by Rayleigh criterion, depth of focus, pitch limit. How quickly, how often can we repeat it? It messes up our resolution because this is general idea how we do that. So we condense light. Now we have opaque regions, transparent regions. We push them through objective lens, gets to resist, right? And once we have all these individual light sources, they are gonna result into a superposition of waves, right? So at any point we'll be getting multiple rays coming from multiple sources, right? So it's not a straight line now. So if I'm a point on the wafer, I'm getting these all sorts of rays coming from different point sources. Make sense? Too much optics? We'll get out of it soon. So, but the idea is that this will result into these specific relations that depend on the numerical aperture of the medium, right? Because of those point sources of light. We have seen this before, right? So where resolution limit, the smallest feature that can be made with the technology depends on K1, which is a constant for specific photoresist, numerical aperture, and lambda. So ideally, if you want to make resolution limit small, we should push for smaller lambda, right? Right? Wrong? So you want to push this down. And numerical aperture is then function of index and acceptance angle, which is from that source, what is the angle, maximum angle through which we get the light that matters for the interference. Right? So this is that angle from that source, what we call as the acceptance angle. So wavelets interfere constructively only when m is plus minus 1, 2, 3. They give us a maximum profile for 5 lambda, for 5 times of the wavelength. Now, if I push the wavelength down, what's going to happen to the feature size?
When it gets smaller.
We can make smaller features, right? But this is going to stay the same. That whatever intensity we get from that, relation is going to stay the same for that.
So we still get interference effects even with X-rays.
If we can have slit where X-rays can see that slit, yes. But the question is there something that X-ray can see as a slit? No, they just pass through everything. Don't they?
So even with lead, with a slit,
If you have that metallic, something that's opaque for X-rays, yes, you will get that. Right? But that, if you're thinking about photolithography or lithography, then you need those special masks to get that image. They're very expensive.
Same applies to electrons also, if I'm not mistaken.
Yeah, anything that travels.
No, you can't find anything that's opaque to electrons. Because e-beam lithography is mainly done by contact printing.
You can't find anything that's opaque to electrons. Oh, there are some things which are opaque.
Not.
So we use those stencils,
Yeah.
mass, to do electron lithography also. It's good. We have stencils or mass for iron also.
Yeah,
But then the question would be a different question. So right now we are talking about photolithography, where we have these lenses, which are made of glass, and we know their optical properties and we know how to control them. If you are shrinking the And we'll see what happens if we push the wavelength really down, what's going to happen to the optics. We can't use transparent optics at all. We can't use glass optics at all. And reason is the band gap energy becomes almost the same as those wavelengths. So we'll see what happens. So numerical aperture is a lens capability to collect all those lights. Of course, depends on this guy alpha, which is the angle that you can accept as many in that region, and n, which is the refractive index. So this is something, I think one of you have chosen this for the paper, immersion lithography, where they use liquids to change refractive index. So now you have medium, which is air, and you have 1 for that. Now if you can change n in that equation, you would want numerical aperture to become small or large to reduce W min. Small?
No, large.
Right?
Large.
It's inversely proportional. Want to make n of the numerical aperture to be a large number. Not possible with air, so a certain limit, but if you change the medium with something that has higher refractive index, we can get that. Right? So it is 0.2 to 0.7 for projection aligners. And this is just way of showing that what are we getting when it's passing through mask and what do we get at the surface of the mask.
So, does the concept of numerical aperture apply when we're doing contact printing? Like, does it degrade to like infinity or 1 or something?
Do you have medium between when you are doing contact with
I suppose, well, photoresist, but yeah,
photoresist? You just transfer your energy right away, right there.
I see.
Contact printing.
So you kind of need a lens
so
for this
medium in between.
to even apply.
Yeah. There's what you see is what you get. There's no diffraction. It's right there. It starts right. So probably your internal reflection of resist might be more prominent maybe than
I see.
this guy. Right. So how can we estimate the resolution of the system? So this is called an airy disk. So we have been looking at those things in 2-dimensional, but actually it's a 3-dimensional thing, right? So that the maxima or minima, the distribution is basically a 3-dimensional thing. So what you get is a point which is maxima, and then everything is going down around it. Now, if I have my feature which was very well defined as square, but what I'm going to get is probably a circle if I'm pushing down the wavelength. So there'll be what is Rayleigh criterion? It's that their 2 images will be just resolved when their airy disk are separated and their energy between them falls to 0. The intensity between them falls to 0. So a point source comes out as a disk, as a region where you have high intensity then around it. So pitch becomes an issue then, because how fast you can make 2 features will become a problem because of the interference in between. So you can't discriminate between those 2. So that's degrading a resolution. So it's not just the feature size, it's the pitch also. How often can we repeat this? There's another concept, coherence. And what happens with diffraction, the feature is shifted from where we want it to be. And there's this quantity called sigma, which should be 0 for fully coherent, and it's very large than 1 when it's called incoherent. So the idea is that everything that falls here is what matters at sigma equal to 0. But that something that falls away from that still imparts energy. So this is what results into that a disk shape behavior. So what do modern steppers do? They adjust for coherence. They have sigma around 0.6 and 0.8 for lines and 0.3 and 0.5 for poles. So that number is much more controlled now with this modern things, modern steppers.
Can you explain more about why the coherence? I think there are different concepts, like traditional coherence.
So
why that is important?
when light is traveling in every direction, so you want that region where all the rays are coherent. They transfer all the energy for your pattern to get transferred. So that's the region in front of the mass where your sigma will be 0. So if you go away from that, that number will increase. Just a factor to define the diffraction.
Okay.
So it's more related to energy transfer.
It's always, why do we want to focus? We always want to have maximum energy transfer. So that distribution is basically the intensity. Right? So it's always this intensity that we want it to be step function on the surface of the wafer. Right? So another factor is depth of focus. So we have probably discussed this a little bit. So depth of focus is the tolerable distance in which we can get the image to be registered within and get the energy transfer to occur. But generally, it's in a layman language, that's the having things in focus, different planes in focus, right? We want with the multiple layers and because of different heights of features, we want the light to be fairly large in depth of focus. So we want depth of focus to be large. But what we see is if you push lambda down to get smaller feature size, we are getting a depth of focus also compromised. Right? And if we are trying to get a numerical aperture larger, we are getting a depth of focus again becoming small, but up to a limit. What should be the limit of numerical aperture? Then it adds up constructively to depth of focus. Okay, let me say it again. What should be the limit on numerical aperture that would be beneficial for depth of focus? You know, and what is good for depth of focus? To have it large. So what should be the limit on numerical aperture? Numerical aperture is a number. Right? So what should be the limit of that number to support a larger depth of focus?
Close to 1.
Close to?
1.
Equal to or less than 1. Because square of a number smaller than would be even smaller number. But if you go above 1, then it's becoming a large number than 1, resulting into reducing depth of focus. So if you are given a problem where you have features at different height and you know the maximum height of a feature on a substrate, that is your depth of focus. That is your minimum depth that you want to transfer or register your pattern on that wafer. Does it make sense? So if you know the height of the tallest feature on your wafer, that is your depth of focus. That is your minimum depth of focus. You have to have depth of focus larger than that. Does it make sense?
So we do run into this problem where the numerical aperture that we work so hard to increase is too large.
You will be compromising your depth of focus.
I see.
right? So yeah, so having numerical aperture large, isn't that a messy situation? Don't know which way to go.
Is it similar to having your f-stop too large, too open in a regular camera?
F-stop.
F-stop is the aperture of the camera where, you know, if you get to a lower number.
Generally,
then more light.
yeah. So generally, would be not expert on optics, but when we are doing a portrait, we do something called a micro setting where everything else goes
Yeah,
out
that
of
actually
focus.
opens the.
But when we
aperture,
put
I think.
the camera on that mountain setting, then everything is in focus, right? You can take, so I think it's called wide lens or something where no, the whole thing comes in focus. Even things close and far, they all are in focus. So I don't know what is the actual setting there, but
It makes it more like a pinhole when you put it in the mountain setting. It
Probably.
makes.
probably I'm not sure what would be, but ideally you want depth of focus to be a large number, right? We want it to be at least the height of the tallest feature, right?
Tallest feature you mean on that layer or in general the tallest feature?
No, on that layer where you are doing lithography, whatever you have on the wafer, you have some feature which is the tallest. So when I say tallest, it's not again just from here to here, it may be something. So now this would be the height that you want to cater for, right? So if you have a feature which is a trench, now and you have to want to transfer some pattern there. So now this is your minimum depth of focus. So it makes sense? Because if it's smaller than that, then registration here or registration here will be messed up. And why is that again? Our light will not be in focus. Not be in focus enough to transfer the pattern, to register the pattern accurately in size, or to expose the pattern completely, resist completely at that space. Make sense? This is along the optical axis over which an image has resist profiles and line width that remain with its specifications. Right? So it has to be within 20% of the peak intensity. Because if you go above and that, we are basically losing energy. And we had that picture there where you had this. If you are here or you are here, you are basically losing energy. Right? So this is where the maximum energy transfer would occur. At this plane is where it would occur. So within 20% is where we can get it exposed. If we don't get it exposed, what do we call that? Underexposed. What if a feature is underexposed? How is it going to show up after development? Blurred. You'll still see resist there in that feature. So it will be exposed maybe halfway, maybe 90%, not all the way. So you will still have resist left behind there, right? So it's called underexposed. You might want to keep on doing development, but it's not going to do anything because that resist at that certain after a certain thickness is not exposed at all. It's not going to dissolve. If you're going to keep on developing more and more, yes, it will be dissolved, but then you will be opening your walls up, right? So that's what is called over development. So depth of focus is fairly restricted number between half of on either side of lambda or n square.
So I think the depth of focus can be controlled by the length between lens and substrate, right?
So basically, that is a number which is set for a particular wavelength. So yes, what you're saying is distance between these two should be a factor there, right?
So if we can control the length, that would be much better.
So we do that to focus it already, right? But the question is that wavelength, how above or top can we still get our registration to work? Of course, we control their distance to focus it to start with. Isn't that what we do when we are looking through an optical microscope? What do we move? We are moving the distance between what? Objective and the slides. That's what we do to bring it into focus. But now question is, depth of focus is something which is on either side of that focus depth. Right? Or focus distance is that depth of both sides of that plane. Make sense? Should be, it's a tricky thing, but needs your vision on to understand depth of focus. So you focus it by changing that distance, but now this is the distance on either side of that plane where you have focused it, where you can get registration to work. So then you play with those and you get this guy, right? So this now tells you playing with lambda is not always the only solution that you get. Not because only this reason, but there are more reasons. We'll see why if we don't want to push lambda too small. So this is something where we can define a number for lambda and play around with these. So one of the thing is that what is the largest numerical aperture you want to limit to still have reasonable depth of focus. So this is just to give an idea that you can have one of them can be in focus, but others can go out of focus. So this is intensity and horizontal distance, and you are seeing defocusing. So if you are not out of focus, you get this guy, but once you go out of focus, yes, you get the intensity to transfer, but then your pattern size is also going to increase in width. Right? Does it make sense? So this is the minimum that you want, because if you don't have it, your width is going to get screwed up. You may not get it developed at all. If you get it, your width will be out of the numbers. Right? So that is just showing feature that we have to make on two levels, right? Above oxide and the level of the wafer. Make sense? How do numerical aperture affect our defocusing level, depth of focus? So it's in microns. If you are going numerical aperture from 0.3 to 0.4 to 0.6, what's happened with my depth of focus? And I'm going from 0.3 to 0.4 to 0.6, what's happening to my depth of focus?
It's decreasing.
It's decreasing, right? So, which means now I don't have too much room, right? Make sense? So, have to find the optimum numerical aperture.
Now that we are doing shallow junctions, does that matter so much?
Shallow junctions?
Like the source is very close to the.
So of course, if your depth of focus is not reasonable enough, and your feature is on that, you are making contact to source, for example, you will get exposure which will be much more wide than what you would have got with this guy. See the intensity? You have much more intensity now. Do you see what I'm saying? So for this guy, now you have your intensity up here, then this guy where you would have your intensity here. So now your resistance is going to get developed. Yeah. And it's going to, if this is the threshold, maybe you'll have a wider line, a wider square exposed where you wanted a small one to be exposed. So maybe you are shooting for 1 micron, but now 1 micron by 1 micron, you will get 1.2 micron by 1.2 micron. Make sense? Unless you focus on that level, then maybe you'll be getting out of focus somewhere else. Right? And 1 to 2 micron is small. It's small, so that your feature will be obviously same scale. And now think about this twist. Right now what we are considering is we are not even touching lambda. Now if you push lambda down as well, this becomes even more prominent. Right? So these are 2-3 equations, and I would want you to know these equations. Remember those equations because they define the relation of light and optics and what do we get as feature size.
So there will always be trade-off between lambda, numerical aperture, and feature size.
Always be trade-off. Yeah. So that's why then we have to come up with out-of-box thinking, which you guys are hopefully doing right now, or not, to solve these things and what else can be done. So right, we need to find again. This was meant for tablet where I could do. So this simple interactions, I'll probably have these for homework. So simple interactions of depth of focus and pitch limit. How do we define those? So with pitch limit, the idea is that we don't only want the acceptable line width, we want to have acceptable sidewall angle as well, right? So we can resolve two lines closer to each other, right? And this is what is showing that if we increase the exposure, our lines are becoming much more angled, so, which essentially results into them interfering, not exposing the whole thing.
Are these cross-sectional image?
These are images taken at an angle. So if that is your reference, these are taken from an angle.
So it's another top view.
So this guy is the top. No, these are side images. Cross section is something where you cut across, but these are side images. So the wafer taken from a side. So focus, exposure, process window. So now we have to then define something called Poisson plot. So this is done by, for a specific technology, these are plotted out. It's a 3-dimensional plot, right? Where you have two entities on X and Y. The third one is written next to the plot. What does it tell us? It tells us what is the depth of focus we can get for what energy to get what line width. So Poisson plot is used to define what we call focus exposure matrix, because we not only want to expose the line to get acceptable line width, we want to expose to have the walls to be straight, right? And we want to have respectable amount of thickness of resist left behind. If you miss any of those, will be out of the size, it will be out of the critical dimension of the feature. Make sense? Why all these things will impact? So if you have more energy, what's going to happen?
The line width increases.
See how does it change? Changes from this. So this is 160. It goes this way. How does it change? Our line width will go up, but our focal position is becoming smaller. It's minus 1.4 to 0.8. So it's increasing on this side.
But line width is
So
It's decreasing with.
So that's on both sides. For your focal, you have to see depth of focus on both sides of the plane, plus and minus.
But the line width is decreasing with increasing.
So this is probably the region where your exposure will work, right? Because away from that plane, you will lose. So depth of focus. Now, you have to think 3 dimensions. I have this plane where I'm impinging my line, right? Has to deliver energy. And then there is some thickness, which is in minus, this is in plus. I'll get only in certain distance, I'll get my energy transferred. Right? At that point, I can make certain width of the line. Cannot make it bigger or smaller than that. Okay, now I increase my energy. I can make a bigger line, and I can make it have my depth of focus is also increasing. Now I can do from here to here, slightly larger than that. So if you put a line here and you say, okay, this is acceptable intensity, then I can make that line. Does that make sense? Have to feel it in 3 dimensions. So I'm changing my intensity, energy, my depth of focus is changing, right? The range which is valid is changing, because if I go too far away from that plane, my line width is becoming 0. Essentially, I'm not getting any exposure. Right? In this case as well, if I'm getting too far away, my line is becoming too wide. So if I'm going too far away from my plane of focus, my line is becoming wide. Now let's go back to this guy. So these 3 things: intensity will give me acceptable line width with acceptable height with acceptable angle of the wall. This is what is called focus exposure window.
Acceptable resist thickness post develop.
So after development, I still am left behind with acceptable thickness of the resist.
But you don't want resist to stay after
I want my resist to stay where it is supposed to stay. Oh, it means where it is supposed to stay.
Oh.
In this case, it was supposed to stay here. It was supposed to stay the whole thickness. But because my lines, my walls have become too angled, I'm losing my resist thickness. You have to digest this guy. How long does it take? You need to understand this part. You will not have to, as process engineer, this will be established for a specific lithography machine. But you might have to measure this up. But given this plot, you should be able to know your process condition. Depth of focus. So if you are given something like that and you're in something like this, you need to figure out what energy will be you would want to use to get that feature. Of course, in that feature it will be given the height and the minimum feature size. Make sense? It will be just a very small window there. Right? So if this is your depth of focus, and this is your line width. So it defines you what is the process window what you can work with, the specific energy of the exposure. I'm using energy, exposure, dose, all things to mean how long that energy will be exposed, right?
The middle line, that straight line, what is that?
That's axis. That is just a line to show axis, to show flatness of this axis here. Right? Because if you don't have that, you would think this is straight, but this is changing. Right? So Boson plant is important to figure out focus, exposure, process window. Now, going back to that question of alignment and registration, we overlay two features by alignment, but once we get it transferred, we get errors which come from alignment error, which would be how close we had brought it mechanically, and then what happens when the light gets exposed. So this is basically the accuracy of positioning, how accurately we can get it to transfer on the wafer within tolerance. Right? So it can be for an edge we have this much distance that we can go, right? Maybe again for between two what you call squares, outside and inside square, we might have certain limitations that we can live with. So these are all these numbers which we would have to know once we are done with our exposure. What happens if we miss register? It can result into failures. What are the failures? What can happen here? If I go from here to here, electrically, what's going to happen? Electrically, what is going to happen? Now, first, understand what is happening physically. So I have a contact, I'm supposed to cover this whole thing, right? So I have this area in contact. But what happens is I cover just half of it. Now, what is going to happen to my contact area?
The resistance will increase.
I just covered half of it. What's going to happen to my contact area? That's my first question. It's half. It's become half. And my resistance is what?
Will increase.
How do we define resistance? What's the formula for resistance?
Resistance will double.
I'm asking, okay, what's my formula for resistance?
Resistivity multiplied by length divided by
Rho L over A. We all know that R equals rho L over A. So my area is half, which means my resistance has doubled. My resistance gets doubled, what happens? If we have designed a circuit to withstand to offer certain resistance, and that resistance doubles, what happens to that machine, to that equipment? Heats up, right? So there's power loss, there's energy loss. What does that heat result into? Failure, right? So ultimately, I'm going to burn away. I'm going to burn down this contact. First step, contact resistance increases, right? Which means there's much more voltage drop occurring in that device, which would mean it may burn up one day, right? So results into failure. Technical word is failure of device. So mean time to failure. There's a specific term used for IC. It's called MTTF, which defines how quickly it's gonna fail. So if we have too much of misalignments, we're gonna get very small MTTF. I miss my tablet. It's just burned on me. Fan is not burning. So this can do that. Or in this case, we have a gate, but since we are not covering it, we're going to get short. We're going to have current passing through from one to the other. And so field oxide. So we do certain tricks to do these, to overcome these problems of registration. We'll probably talk about it next lecture. So there are certain tricks which we do to make our registration to accurately depict the end product. Those tricks may be sometimes overshooting a feature size. So making a feature bigger, or putting some boxes and edges, so when we register it, we get sharp corner. So there's multiple. We might place some dummy features somewhere, so we'll expose them just to have a uniform process going on. So there's many things what we do to may have a good registration. So we'll look at those next Tuesday. Questions? Again, Monday is the deadline, right? So Blackboard is preferred mode of communication for that chapter, for that
Monday till noon.
term paper. No, 30 minutes after noon. So, all right? Questions? I'll see you on Tuesday.